Okay, Lamai. This is going to be a very little discussion about the melting and boiling point variations, right? Okay, so as you see here, right, this kind of some chart, right, and you can see some questions are also appearing here. So if they have asked this kind of question, right, to come up with the melting point trend with giving you some compounds or some metals as well, some mixture of stuffs, right? So how to comment on those, right? How to come up with a good answer for this kind of a trend, right? That is what we are going to discuss now, right? So okay, so first of all, when you see some compound, so some chemical species appearing, which are to actually which you are supposed to um, arrange in order of the melting points, right? Okay, first thing you should do is first you have to select which kind of a species you are dealing with, or which kind of a set of rules you have to apply to comment on their melting points, right? Now that is what we are going to discuss today, right? Okay, so it's like this. So basically, when we are referring to chemical species, right? We have three types of basic chemical species: the metals, the sodium, magnesium, calcium, strontium, or zinc, iron. So those are metals, right? Chromium, aluminium, metals. So to discuss about the melting points of the metals, we have to consider the metallic bonding strength. So we know that melting point is all about, right, the heat energy or the temperature we need to supply to put the particles apart from each other in melting. But that is what happens now. The closely bound solid particles will move away from each other to convert to a liquid. So by supplying the heat, the temperature, what we are doing at the melting point is actually we are trying to put the particles apart from each other. For that, the strength of interaction between particles matter, right? That is why we have to consider the strength of interaction or the type of bond between the particles which connects them, right? So if you are dealing with metals, right, we have to consider the metallic bonding strength. We have to consider metallic bonding strength, right? So if the metallic bonding strength is high, you need to supply some greater amount of heat, temperature to put them apart by breaking the bond, right? So if you are considering about metals, you have to apply the rules with the metallic bonding strength, right? If you are with a greater number of electrons with electron C, your metallic bonding strength will be high, so that the melting points will be high. If the radius of the cation is low, your metallic bonding strength will be high, so that the melting points will be high with such kind of metals. When regarding to D elements, if the ionization energy is low, you can release more number of electrons to the electron C, so that your metallic bonding strength will be high. That will lead to a greater melting point, right? Okay, that is all about metals. If you have to compare NaCl and magnesium chloride, sodium chloride and magnesium chloride, and calcium chloride, like that, the ionic compounds, magnesium chloride Mg2 plus Cl minus, the sodium chloride Na plus Cl minus, the calcium chloride contains the Ca2 plus and the Cl minus, right? So the ionic compounds, if you are supposed to compare the melting points of those ionic compounds, right, we need to apply the theories related to ionic bonding strength, right? The Fajan rule, right? What happens when the cation's charge is high and the radius is low? The cation's porosity power will be high, as well as with the anion, if it is with a greater charge and a greater radius, its porosity will be high. That will leads you to kind of some greater covalent character and some weaker ionic character in your ionic bond. So the ionic bond strength will be low when these things appear, so that your melting points become low, right? That is what the Fajan rule says, right? So when the ionic bond strength is low, for the ionic compounds, the melting points are low, right? So those rules should be applied if you are to compare some ionic compounds, right? The melting points of some ionic compounds, right? Then finally, if you are dealing with covalent stuff, the CO2, H2O, H2S, the covalent compounds, The atoms are bound via covalent bonds. The carbon graphite, carbon diamond, those are also coming under covalent stuff, covalent species. The atoms are bound via covalent bonds. Here the atoms are bound via metallic bond. Here atoms are bound via ionic bonds. Here via covalent bonds. The atoms are bound together, right? For those stuff, right, we have two kind of things, right? So we have giant covalent lattices, right? So atoms are with a network arrangement, the giant covalent lattices, the homoatomic lattices and the heteroatomic lattices, right? So, and then we come up with the molecular lattices. There are two kinds of lattice structures with the covalent stuff, atomic lattices as well as the molecular lattices. So, basically with atomic lattices, the atoms are or the particles are connected via strong covalent bond, which is referred to as a primary bond, right? These three kinds are primary bonds, right? In these three situations, the atoms are connected via primary bonds. So that is what we see with the atomic lattices. The atoms are bound via strong primary bonds, covalent bonds. But when it comes to molecular lattices, the atoms are, or the particles, not the atoms, the molecules. The molecules are bound via secondary interactions. Secondary interactions, some weaker forces compared to these three stuff, right? So always the secondary interactions are smaller than the primary interactions, right? So that is the general trend, right? So with the molecular species, you have these rules to apply, right? So when it comes to molecular species, right, these rules could be applied, right? So when deciding the molecular weight, two factors matter for the molecular species, right? Like H2O, H2S, right? HCl, right? Kind of stuff, right? NH3, HF kind of stuff. Other than these guys, all the covalent stuff comes under here in our A-level syllabus. That is okay to handle like that. Other than these few stuff available written here, all the other covalent compounds, covalent guys, can be taken at this stage, right? So which are bound via secondary interactions. So they are when the molecular weight difference is greater than 50 units, the molecular weight matters, right? When the molecular weight is high, the melting points will be high. So, and if the molecular weight difference is less than 50 units, like H2O and less than 50 units, like H2O and NH3, in such situations, only H2O and CO2 less than 40 units of molecular weight difference, they are secondary strength matter, right? Greater secondary strength, melting points and boiling points are higher. That is the normal idea. Let's use this stuff to comment on this kind of a question or come up with a better answer for this kind of a question. Let's use the things we have learned there, right? Okay, this one. So we have to compare the NaCl, H2O, HCl and CbR4. First of all, what you need to do is just categorize these guys, right? To here, here, to here or here, right? Okay, just categorize the guys. Whether we have to apply the rules related to metals, or whether you have to apply the rules related to ionic compounds, or this thing, or whether you have to apply the rules related to the molecular species, right? See, NaCl. NaCl, it's a ionic compound. NaCl is kind of a ionic compound, right? Ionic compound. And these guys, non-metal combinations, non-metal combinations, non-metal combinations means covalent compounds. The ionic compound is metal and a non-metal. Covalent means just non-metal combinations. Metals means just the metals are appearing, right? So non-metal combination. So it comes under covalent compounds. But you don't see any of these available there. So all of these are covalent compounds coming under molecular lattices. So here the rules related to molecular lattices should be applied. Molecular lattices could be applied, right? So first of all, with molecular lattices, you are connected via secondary interactions. Secondary interactions. Secondary interactions. So always the primary interactions are stronger than the secondary interactions. So we can say the NaCl is coming up with a greater melting point than all of these, as the primary interactions bound strongly with the primary interactions, the particles are bound strongly compared to the secondary interactions, intermolecular forces, right? Normally, secondary interactions are coming up with delta charges now, right? So, primary interactions coming up with complete charges now. So, the primary interactions are normally greater with strength than secondary interactions. So, the NaCl particles will be bound heavily, strongly compared to these guys, right? So, NaCl will carry the greatest melting point out of these four. Then we comes with the molecular lattice forms, right? So we have to apply these rules here, right? We have to apply these rules, right, to comment on these three guys. See here, first thing to look at is the molecular weight factor. Molecular weight factor. Here, when it comes to these four guys, three guys, right? This guy's molecular weight is like 18, right? HCl is coming up with 35, and this thing is 36.5, right? But here, Br is kind of 80. One Br carries 80. That into 4, that means 320 and 334, 332, right? So with the molecular weight factor, this guy is clearly wins as it guys exceed 50 units of molecular weight than these two guys. So with the molecular weight factor, the CBr4 comes as the greatest melting point species out of these three, right? Okay, because its molecular weight exceed 50 units than the other two, right? Right now, these two guys. Now we are remaining with H2O and HCl. So now those guys are with less than of 50 units of molecular weight. So we can use this, right, as second intrinsic strength to come up with the melting and boiling points. Here the H2O is with hydrogen bonds, while the HCl is with dipole-dipole interactions. This is with hydrogen bonds, while this one is with dipole-dipole interactions. So the hydrogen bonds wins than dipole-dipole interactions with the second interaction strength. So when the second interaction strength is high, melting and boiling points are high. So the H2O is with a greater melting point as it carries some hydrogen bonds compared to the HCl, which is with some dipole-dipole interactions. So that is how the answer is made for this question. Right now? Okay. Let's come up with the next one. The sodium, calcium, H2O and CO2. First of all, you have to categorize these guys under here, right? Sodium and calcium. Sodium and calcium both are referred to as metals. Both are referred to as metals. Sodium just a metal appearing, calcium just a metal appearing, S and D block, all the S and D block elements are metals, right? And these guys, covalent stuff, only the non-metals are appearing, the covalent stuff, and won't comes under here, so that we can say those are coming under molecular lattices. Molecular lattices. Molecular lattices. Molecular lattices. Then always the metals are with, normally metals are with greater melting and boiling points than the ones with molecular lattices. What is the reason? Because here the particles are connected via a primary interaction, the ionic interaction, the metallic interactions, primary, which is primary interaction, and here the particles are connected via secondary interactions. Secondary interactions, right? Always, normally the primary interactions are stronger than secondary interactions. So you have more strong interactions between the particles, connection between the particles. So you need some greater heat to put them apart compared to secondary interaction situation. So these two things should come with a greater value. Like here, sodium and calcium should come here, then the H2 and CO2. That is the first suggestion, right? Okay. Then what we can do? First, compare these two guys. Sodium or calcium. Which one wins? We have to apply these rules, right? So with sodium, you are just releasing only one electron to the electron C. But with calcium, you are releasing 2 electrons to electron C. 2 electrons to electron C. So calcium wins and sodium loses there. So calcium wins. So one may think of that the sodium is with a smaller radius having only 2 electronic shells and calcium means it's a greater radius. That is okay. But in order you have to concern. That is the idea. In order you have to concern. First concern this one. If you can't come up with the answer with this point, then go for the other one. If you still can't come up with the answer with that point, then go for the third. That is how we are supposed to come up with a good answer. So first point is the electron released to electron C. 2 electrons will be released by the calcium when it forms calcium 2 plus, but only 1 electron by the sodium. So with that first point, calcium wins. The charge matters heavily than the size, right? So calcium wins than the sodium, right? So calcium is with greater metallic bonding, so that melting points will be high with the calcium, right? Next one, H2O and CO2. H2O and CO2. So we know H2O is with hydrogen bonds, CO2 is with London forces, and the hydrogen bonds are stronger than London forces. Hydrogen bonds are stronger than London forces, so that H2O wins over CO2. H2O wins over CO2. Right now, that is how we are supposed to come up with the answer. Right? So this is how we need to use the separate set of rules for separate particles we are dealing with, right? So first you have to consider to which section your considering particle, considering substance belongs to. Then you have to apply the correct rule set, and then you can come up with the final answer, right? That is how we are supposed to comment on the melting and boiling points of the substance, right? Okay, right. Then that's it for today. Let's after this section we are going towards the third unit in the next class. Until then, thank you and goodbye.